So in this video we're going to cover the material which is needed for this week's lab. And in this week's lab we're going to do two different or cover two different topics. The first topic is how do we perform chi-square test for association as well as the chi-square goodness of fit test. The second topic is actually how do we deal in R with the normal distribution. Specifically, we're going to use commands to calculate probability for random variables that are normally distributed. So just to start, right, every time I'm going to navigate on my computer to the folder where I keep all my script for this class, right? It's right here, Spring 19. I'm gonna open it, okay, and then I'm gonna set it as my working directory. Remember, set this as a working directory, right? Now I'm gonna open a new script, our script, and as usual I'm gonna call it bio 430 530 spring 2019 lab 5. Okay, and I'm gonna save it, save as over lab 5, and here we are. Okay, so in this script we will introduce chi-square test in R as well as working with the normal distribution. Okay, so as usual we're going to clean up our workspace. I'm going to use the remove list equal ls command and run it. If you guys want to run it, do you remember you can just select and run it, and if you check your environment you see that there is nothing there, right? And then I'm going to import some packages. Import packages, right? So if you guys remember, I'm going to say library mosaic, library ggplot2, ggplot2, library car, and library scplot. Right, so I'm gonna select them all and run them. Okay, and they're all nicely loaded as you can see from here. So the first thing, let's do the goodness of square test. Chi-square goodness of fit test. To do that, we usually use the so-called function chi-square dot test, right? So if you guys are not sure, you can just do a question mark chi-square dot test, and you're gonna open your help here, right? Where basically requires your observation, which is and then your p, which is your null probability, if you want to do a chi-square goodness of fit test, right? So just to go in an example, if you guys remember the problems of snails nesting on west, north, west, south, and east, right? So we observe observations. We see that there are 26 snails that are on the north side, 6 on the west, 2 on the south, and 44 on the east, right? We know that our null model, right, is that they should all nest in the same equally, right? Null model probability. So the idea is, so your probability should be reparted as what? 1/4, right? 1/4, 1/4, and 1/4, right? So you should expect a fourth of snails north, a fourth on the west, a fourth on the east, and a fourth on the south, or vice versa, right? This is the null probability model. Okay. And so to test the probability that there is no preference in slope, right? We ran the so-called chi-square dot test, where you use as your observations, and your probability P is your null model probability. Okay, sorry. So you select this, you run it, and you get an error. Why do you get an error? Because here, I'm sorry, I forgot this. Okay, so let's do that again. You run it, and what you see, right? You see that the chi-square test for given probability tells you that you get a chi-square of 58, you get 3 degrees of freedom, right? 4 classes minus 1. The p-value, which is the probability of seeing this outcome from a null model that should be uniform distribution among the 4 directions, it's super tiny. It's e to the minus 12, right? So it's highly, highly, highly unlikely. Okay? So let's do now the goodness of fit for the example of the baobab trees, right, in the desert, right? So if you guys remember, right, we have, let's make actually the observation, right? So let's make the observations that you would have recorded in the field, right? Is to do this, is use the command rep. X, let's call it X equal rep 0 and 5, comma C 35, comma 28, comma 15, comma 10, comma 4, comma 3, right? Let's run it. Let's go here, X baobab example. So this is kind of like what's your field notebook you look like, right? So if you table this, if you do table of X, right, you actually have your distribution, right? I have 35 plots with no tree, 28 with 1, 15 with 2, 10 with 3, 4 with 4, and 3 plots with 5 trees, right? And you can actually do bar plot table of X, right? And you see the distribution of your plots, right? Okay, great. So we want to know, is this random? Is this distribution random? Which means also, does it follow Poisson? Is this event random? Maybe it's better. So what do, right? We don't know what's the we do not know the average number of trees per plot. So we calculate. Right? And how do we do it? So we call it with Poisson. Let's call it the lambda. For Poisson, lambda poise, it's equal to mean of x. And it's about 1.25 here. Okay, great. Okay. Now, let's call the Poisson probability, right? Probs, right, which is my known model, is what? Is d poise 0 to 5, right? Comma lambda. Let's call it probs poise. Call lambda poise, I'm sorry. Right? Right? This is the probability associated to have no tree, 1 tree, 2 tree, 3 trees, 4 trees, and 5 trees. Right? And now we need to add 2 more things, right? We need to add the fact that my observations, right? I do not see trees. I do not see plots with more than 5 trees, and so basically my observations trees it's this vector plus 0, and to my probability of Poisson, right, I'm gonna add I'm gonna basically evaluate the probability of 6 or more trees, which is gonna be equal to what? It's called complementary, complementary, which is equal to 1 minus the sum of the Poisson probability, right? It's complementary, which is 0.018. So this is the probability that I would see 6 or more trees, right? And in my observation, I don't see any trees, any plot that have 6 or more trees, right? So now I can run the test, right? I can say, first of all, I overwrite my probability Poisson by concatenating how it was before and is complementary. So my Poisson probability is this now, and then I can run the chi-square test. Run chi-square. So I say chi-square test using observation trees with the probability, which is given the prob poise, right? It tells you that the we have 6 degrees of freedom, right? And p-value is 0.03, right? So this is slightly different than what you do in class, in where you actually reduce 1 degrees of freedom here. Basically the concept is pretty similar, right? The calculations are the same, and R gives you an approximation, because R doesn't know that you have used one of your observation to estimate the Poisson variable, okay, the lambda variable for the Poisson distribution. Okay, so let's now let's now import the data frame, the people data frame. So I'm gonna go into my files, and I'm going to, there's a people data frame in my courses, and then I'm gonna put it in my working directory. Okay, so I'm gonna go here, open folder, and now I should see the people data frame appearing. Okay, so let's read the people. So read in people data frame. Okay, people read.csv, people.csv, right? So if I do people, we see all this blah blah blah, right? So the first question is, are accident and driving ability associated, right? So we're gonna use a chi-square test for association. Okay, so how do we do it, right? Let's make a table. People table is equal to table, right? People accident, people driving, and let's print it, right? This is the number of accidents, and this is the classification, self-classification, average, good or bad driver, right? Are the two variables associated, right? So how do? We run a chi-square test, okay, and we feed the people table, right? And what do we see, right? Chi-square value, 6 degrees of freedom, p-value, it's really high. So based on this data, there is no relationship between driving ability, or at least in this subset of population, and the number of accidents that they have encountered in the last year. Okay, so I'm gonna stop for now, and I'm gonna make another video now for the normal distribution.